Alright, this is 12.1 in Advanced Geometry, and today we'll be talking about prisms and cylinders. A prism is a three-dimensional shape with polygons for a base. So remember, a polygon, it has to be made up of segments, and it's closed, it intersects. It can't have a circle or anything like that for a base. So these are the two bases of this prism right here, and they got to be exactly the same. They're congruent bases, and it's three-dimensional shape. And a cylinder obviously has circles for a basis, so that's why it's a different idea. But congruent bases right here, okay? And to name this prism correctly, there's four concepts involved. Number one, you tell me if it's right or oblique. Right means it's going to be straight up and down. You know, these edges right here, these lateral edges, are perpendicular to the base, and you can tell with the right angle box. So this is going to be right. Then you tell me the shape of the base. Well, the base right here is a triangle, so we'll say that it's triangular, and it is a prism. You'll have to put that word because in a few days we'll talk about pyramids and cones and stuff. So it's a right triangular prism. And then the fourth thing to tell me is if it's solid or surface. Solid means it's made of the same material all the way throughout. Surface means it's like hollow on the inside, and you can tell in the drawing if it's solid they shade it in, and if it's a surface they leave it clear. So this is a surface. This is a right triangular prism surface. Four things to tell me: right or oblique, shape of the base, pyramid or prism, solid or a surface right here. So those are the four things. Next guy right here. First thing to tell me, right or oblique. And you can tell just by looking if it's got a right angle box in the picture if these lateral edges are perpendicular to these base edges right here. So you can see that there's no right angle box, so this is oblique. Then the shape of the base has 6 sides, 1, 2, 3, 4, 5, 6, so that's called a hexagon. So we'll say it's hexagonal, and it is a prism, right? All of these are prisms today. We're not dealing with any pyramids. And then the last thing, solid or a surface, so this puppy is a surface. Why don't you pause the video and give number 3 a try on your own. And that's a right, because you can see the right angle box, pentagonal prism, and it is a solid because it's shaded in. Right? So shape of the base has 5 sides. That's a pentagon. To actually draw these indicated surfaces, we will need our geometer, and to draw a right cylinder, the shape of the base is a circle. So we have these three-dimensional shapes. We're not going to use any of the shapes on like 1 through 20. If you look at the numbers on your geometer, 1 through 20 are all two-dimensional shapes. Down here, 21, 22, 23, 24, those are our polygons looked at 3 dimensions. And 27 and 28, we need those also. Those are our circles in 3 dimensions. So take shape number 27 right here, and let's draw it like this. Let's draw, I'm going to freehand it. Let's draw it solid on the front side and dashed on the back side. This is the bottom of our pyramid, or excuse me, this is the bottom of our cylinder. Wow. This is the bottom of our cylinder right now. So take shape 27, but don't draw it all the way around. Solid on the front side, dashed on the back side. Then slide straight up and draw the entire shape 27 solid. This is the top of our cylinder right here. And then just take a straight edge and connect straight down and straight down. And then since it's supposed to be right, here's what we do. We put the center of those bases, the center of the circles, in here with a nice dot, and we'll connect from here to here and put a right angle box. That is a right cylinder right there. So the shape of the base is the circles. They're the same size, so make sure you use the same one each time, and straight up and down. In oblique triangular prism, we need the triangle that's 3-dimensional, which is shape 21 on our geometer. So we'll start by drawing that, and draw the front side solid and the back 2 sides dashed for me right there. So this is the bottom of it. Then, since it's oblique, we'll take our geometer and slide it straight up and over just a little bit, and we'll draw that same shape again, all solid. This is the top side. Then you take your straight edge and you connect these 2 guys together with a nice straight edge, and these 2 guys together. And then on the back side, you do a dash, because it's like you're looking through the object, and it takes a while to get used to what this thing all looks like. Some people's eyes work better than others, but it's an oblique triangular prism. I have some 3D shapes that you can see like physically in person. It makes it a lot easier to see. But this is oblique because it doesn't have a right angle box, triangular prism, and then since they didn't say, well, I guess they did say surface, they said that in the instructions, so we won't shade it in either. And then the last one, it says draw a right prism whose base is a pentagon, so that will be shape 23. Let's draw the bottom one first. Oop, my bad. Let's draw the bottom one first, so take my straight edge, and I'll draw it like so. These three guys solid, and these other two guys dashed. They're shape 23. Sorry. Then slide it straight up and draw the same thing again. And then connect all your edges together. These four will be solid, and that will be dashed right there. And then since it's supposed to be a right prism, we need to put a right angle box in here. And I keep talking about these types of edges. Aren't these guys right here on the base? Like a prism has two bases to it, right? It's got a top base and a bottom base, so these are all base edges right here. And then these up and downers right here, these are what's called lateral edges. You know, they're the edges of the sides right here. Lateral means sides, so there's lateral edges and base edges, which we'll talk more about next time, but just so we kind of get the same lingo, like the base edge versus a lateral edge. So all the red ones, let's finish it off, are base edges because they're edges of the base, and all the green ones are lateral edges. So it's in the box at the right. Well, a box is a fancy name for a right rectangular prism. So that means that this is a rectangle for a base, and it's a prism, and it's right also. So we got a right angle box all over the place. All of the angles involved with it are right angles. You can see there's one right there. There's going to be one right here. Everything is a right angle. All angles are right angles here. It says in the box at the right, the distance from H to A is 5, so put that in your picture. Distance from A to B is 8. Put that in your picture. And distance from B to C is 15. Very handy to put information in the picture. It says find the distance from H to B. Let's draw that in with our straight edge. Distance from H to B. And as you can see, we get a little right triangle formed right here. This shape is a right triangle because that angle down there is a 90-degree angle. So we have a right triangle. What we're missing out of this is the hypotenuse, so let's do a little work. Let's do the Pythagorean theorem. 5 squared plus 8 squared should equal the distance from H to B squared. And then 5 squared is 25. 8 squared is 64. And that's still equal to H to B squared. So that's going to be 89 equals the distance from H to B squared. And since 89 is not a perfect square, distance from H to B equals the square root of 89. And then we want to put that in the picture. Square root of 89. Boy, I really missed that. I don't even care if this radical can simplify in this chapter because we'll learn here how we're going to reuse these answers, and you'll just see here shortly. So even if that could simplify, I could care freaking less about it because it's not going to do us any good to simplify those radicals. So find the distance from H to B. It's the square root of 89. Then we'll approximate that in our calculator also. It's just kind of good to know. It's like, well, how long is that? So square root of 89, punch that in. It's about 9.4 units long. Then the next thing they say, find the distance from H to C, which now we're starting to really get some messed up pictures. It's like, whoa, I don't really see what's going on here. So distance from H to C is when we connect those together. And as you see right here, I have kind of highlighted the triangle that we have. This is a right triangle. You're going to have to trust me on this. It's just kind of leaning back a little bit. It's in this plane that's going diagonally right here. But this is still a right triangle. And we have a leg right here at the square root of 89. And we have another leg in 15 right there. And we're looking for the distance from H to C, which is that hypotenuse. So I've got square root of 89 as a leg, and that needs to get squared. Plus 15 squared should equal the distance from H to C squared. And this is why I could care less about simplifying that radical, because we're probably going to end up using that radical in another Pythagorean theorem, and it's just more handy to have this square. This is just a square root, because the square and the square root cancel each other out. It's so much easier to square that than to take, like, say, 2 square roots of 2 and try to square that and get 8. It's just like, whoa, that's not as easy as you think. So leave it as unsimplified, and then 15 squared is 225. And then we'll equal the distance from h to c squared. Add those together. 89 plus 225 is 314. And that equals the distance from h to c squared. So the distance from h to c equals the square root of 314. Always finish your work right here. Don't just put the answer up here. So square root of 314, and then we'll approximate that. About 17.7 units long. Name the vertices. Well, the vertices are the points. They're all the points that make up the box right here. So I'll grab my blue highlighter, and that's like just this point, and this point, and this point, and this point, and this one, and this one, and this one, and this one. There's 8 different vertices that make up this box, so they're just the points, and points are always written as capital letters. So it's A is a vertice, B, C, D, E, F, and G, and H. Make sure you got 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And since they were alphabetically arranged, I put them in alphabetical order. There's no particular right order to put them in, but why not put them in alphabetical order? So those are the vertices, just the points where all the edges intersect each other at. Name the faces. Well, there's 6 faces to a box. Here's 2 of them. The top and bottom guy are faces. Those are rectangles right there. So you can see a green face and an orange face, if you will. Let me name the green face for you. It's any order you want to put these 4 guys in, as long as you go consecutively. So how about H, E, F, G. You see how I went H, E, F, G, nice and consecutively. You could go E, F, G, H if you wanted to. You could go F, G, H, E. You can go E, H, G, F. You can go counterclockwise if you want to. You just can't skip around and go like H to F to G to E. You can't cross up. You got to go in consecutive order. So that's the top green base, E, F, G, H. Bottom one, A, B, C, D. There's 2 faces right there. Here's another 2. So I like to go in some sort of order. I did the top and the bottom. Now what I want to do, I want to do the left and the right. The left and the right. So HGBA is the left guy. HGBA. And EFCD. So I did top and bottom. I did left and right. Now I got to do the front and the back. So the front one is the orange one here. That is GFCB. And the back one is HEDA. As long as you go in consecutive order. DA, HEDA. So there's all 6 faces of this puppy. Name the edges. The edges are like just the segments that make them up. So where's my highlighter? I like to go in some sort of nice order. I like to get all my left and right ones. So here are 4 edges so far. Aren't all these guys going like horizontally, like left and right, if you will? And the thing is, it's not HE, it's segment HE. The edges are segments. Segment HE, segment GF, segment AD, and segment BC. So there's 4 edges right here. Now let's get a new highlighter, and I'll get all my up and downers. 1, 2, 3, 4 up and downers, if you will. Segment AH, green. Segment GB, segment ED, and segment FC. And there's still some more edges. I need to get all my kind of like slanties, if you will. That's right here. This dude, 1, 2, 3, 4. There's 12 total edges per box. So segment H, blue, 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 blue. Segment HG, segment EF, segment DC, segment AB. So 12 edges. Because the shape of the base is a rectangle, right, since that has 4 edges, you just take that times 3 is the rule, because you'll have 4 on the bottom, 4 on the top, and 4 up and downers. In the oblique cylinder, what is the height? That's tricky because people think the height should always connect these two things together. No, height has to be perpendicular from the top base to the bottom base. The height is straight up 22 units. What is the area of the base? Well, the shape of the base is a circle, and the area of that is pi r squared, so the area is exactly 25 pi. Alright, you square the radius and stick a pi with it, so you get 25 pi. Then we can approximate that with our calculator. About 78.5 units cubed, squared, my bad, it's an area. Holy cow. Then it says, use the right hexagonal prism at the right. Name the bases. Well, the bases are the hexagons, because that's pretty obvious right there. Here's one of them. So we name it in any consecutive order that we want to, right? So we call it L, K, J, I, G, H. You don't put any commas in there. They weren't asking for the vertices. They were asking for the name of it. You name a polygon by its vertices in consecutive order. There's one of them. The other one is A, B, C, D, E, F. So there's the 2 vertices. It should have 6 letters in each one of them because it's a hexagon. It's got 6 different vertices. Name the lateral faces. The lateral faces are the faces left that are not the base. So I'll highlight one of them for you. Aren't they all rectangles right here? So here's one of them, LGFA. Why don't you pause the video and get the rest of the lateral faces? There should be 6 of them, right? Since this has a hexagon which has 6 sides, there should be 6 lateral faces. So here's one of them and 6 of them. So we have LKBA as one, KJCB, JIDC, HIDE, and GHEF. Total of 6 plus the one that I gave you to start with. Name a pair of edges that are not coplanar, not in the same plane, so they got to be skewed to each other. So first thing you got to do is pick an edge, any edge. There you go. There's an edge right there, just at random. Segment LK. Pick that one. Then I got to find me another edge that's not in the same plane as it already, and it's not going the same direction. So you can see that this one doesn't work, right? They're going the same direction. Even this one doesn't work because you can have a plane, if I could sketch a little bit better, you could have a plane that you connect those two together with right there, and they're still coplanar. So they can't be in the same plane and they can't be going the same direction. So this one doesn't work either because they're in the same plane of this base right here. You got to pick something like this guy right here. That's totally going a different direction whatsoever, and it wasn't in the same plane as that dude. You can't use this one because it's in the same rectangle right here, so it's got to be like going a different direction and not touching it is basically the way it goes. So segment HE is another example. Here, let's start over and let's try again, right, just for fun, because that was just an example. It says name a pair of edges that are not coplanar, so let's just try another one. Let me start by picking this guy right here. There's an edge. Now I got to find something that's not touching it and not going the same direction. So this guy, right? Isn't that not touching it and not going the same direction? So there's a ton of different answers that you could put on this one. Name the real-world object geometrically. A box. So it's back to what we did like on the first few problems about if it's being right or oblique. And a box is definitely right. It's rectangular. The shape of the base is a rectangular, and it's a prism. And the question is it solid or surface? You know, well, it's surface because the idea of a box is to try to carry something. So a box is a right rectangular prism surface. because that's what they're designed for. If it's oblique or anything, it's not really a box. A paperback book. Think of like a brand new one, right? Is it right or oblique? Well, when they originally make them, they're nice, neat, perfect right angle, so it's going to be right. Shape of the base is a rectangle, so it's a right rectangular prism. The question is it solid or surface? Well, a paperback book isn't the inside made all of paper, and the cover's made of paper, so it's more of a solid than it is a surface. A right rectangular prism, solid. Can of Mountain Dew. The shape of the base is mostly a circle. You know, it's not a perfect, yes, that is a circle, but this is like a cylinder. It's not a perfect cylinder because of the cool little thing to put your lips on and everything and all that weird stuff, but it's most like a cylinder, so it's a right cylinder. And then the question is it a solid or a surface? Well, the can is made of aluminum, and even though it could be full of Mountain Dew, the whole idea of it, so you get the Mountain Dew out of it, this is a surface. It's a right cylinder surface. And when you describe things that are cylinders, you don't need to put like the right circular cylinder. The word cylinder understands that the shape of the base is a circle and it's a prism right there. So it's right cylinder surface. And then a videotape box, it's still a box, so it's a right rectangular prism surface. Final one here, find the indicated lengths. If they don't have these dimensions in your picture, put them in there that this is 12 inches, 7 inches, and 17 inches. Find the distance from G to E. Okay, well let's draw that in with our straight edge from G to E, wherever G is, there it is, G to E. And remember, this is a box right here. If it doesn't say so, I guess we're assuming it, because there should be a right angle in there somewhere. And this is a cool little right triangle, so that's what we're finding right here, this guy, with a nice neat right triangle. This is the hypotenuse, so 7 squared plus 17 squared should equal the distance from G to E squared. 49 plus 289 should equal the distance from G to E squared. And then we add those together. 289 plus 49 is 338. So this is from G to E equals the square root of 338. Put it in the picture. Square root of 338. Then the next thing they want us to find is the distance from D to F. So here's the right triangle that is formed here in blue, because this is a right angle right there. So we'll do a little 12 squared plus 7 squared equals the distance from D to F squared. 144 plus 49 equals the distance from D to F squared. Add those together. 193. Square root of 193 is what the distance from D to F would be. Put that in the picture. Then the next thing they want me to find is the distance from D to G. So drawing that in, you get a couple of different situations. You could use this green triangle right here, which is the one I prefer the most, using this as a leg and this as a leg, and that's the hypotenuse, because here's your right angle. I know that's difficult to see, that that's a right triangle right there, but it is. So it's the square root of 193 squared plus 17 squared equals the distance from D to G squared. Square root of 193 squared is 193 plus 289 equals the distance from D to G squared. 193 plus 289, 482 equals the distance from D to G squared. And the distance from D to G equals the square root of 482. And the other right triangle you could have chosen, if you didn't want to use this green one, you still could have found it by using this green one right here, where this is 12 and this is the square root of 388, and you'd still get the same thing. It doesn't matter if you use this one or that one, it all works out the same. But this is the more popular one you'll see on homework questions and everything, so that's why I asked you to use it. So, let me know if you have any questions, and have a good one.